Welcome back to another lesson. Previously, we looked at various ways of making predictions with a linear model using PyTorch, and worked our way up to a more standard way, that of which will be implemented going forward. Before we start discussing the machine learning concepts involved in training our model, before we even train our model to fit a dataset, we must actually create this dataset first and plot it. As such, we will keep this video short. If you wish to skip this preliminary step and simply move on to the next video where we train our model, I've included the source code in a subsequent article, as well as on GitHub. Otherwise, if you wish to follow along, feel free to use this earlier notebook as a starter project, as we will be simply building over it. Firstly, for visualization purposes, we begin by importing matplotlib.pyplot as plt, as we have always done before, and instead of pressing Shift and Enter to run the cell, press Alt and Enter to create a new cell right below, as it is in this cell that we will be creating our dataset. Ultimately, this is the dataset that we will try and fit a linear model into. Our dataset is plotted on a two-dimensional coordinate system, such that each data point is characterized by an x and a y coordinate. As such, we will be specifying the x values for our data points, which we will set equal to torch.randn, and what this does is it returns a tensor filled with random numbers that are normally distributed. This function accepts a sequence of integers which define the shape of our tensor. We want our tensor to have 100 rows and 1 column, such that there will be 100 points, and each point has a single value within the normal distribution. If we print this value, print x, it outputs a tensor filled with numbers that are normally spaced out. However, the numbers are relatively small since they are centered around 0 with a small variance. So what we can do is multiply all the numbers in the scalar by a value of 10 times 10 to set up a larger range. As we are dealing with a two-dimensional coordinate system, each data point will have both an x value and a y value, which we will set equal to the output y. For now will simply be a function of x. To further modify the y value, let us simply plot our current set of data points with plt.plot x. Recall this must be converted to a NumPy array, and the y value as well, y.numpy. And we want each data point to show up as a circle. So what we can do is just place the letter O as our third argument, O, not 0. Outputting this should result in a straight line of data points. This was to be expected, such that all data points are normally distributed within the x. All right. Now, fitting a linear model into a straight line of data points would be relatively easy. We will challenge our model by adding a bit of noise to our output. To each y value of the point, we want to shift it upwards or downwards, such that the noise is also normally distributed across the entire range. So instead of just setting the output equal to the input x, let us add this normal distribution of noise to all 100 points by adding torch.randn 100 to 1. And recall that randn will center around the 0 with a relatively small standard deviation. We want data points to be relatively spaced out, so we want the noise to be reasonably significant. As such, we'll multiply the noise ratio by 3. 3 times torch.randn, and this should create our noisy dataset. All right, now for aesthetic purposes, or actually for clarity, let us assign the y-axis a label, plt.ylabel, y. The x-axis as well, plt.xlabel. All right, and we are good to go. We have our noisy data, and now that we've created our data set, it is time to train a model to fit this data set. Seeing that we've already done the code for creating a model, we will reuse it. This linear model that we currently have, it has random weight and bias values. Random parameters assigned to it from the linear model. One can only assume that this model does not fit our data well. All right, well, let's see for ourselves. What we'll do is we'll create a new cell. Or you know what we'll actually do is just delete what's inside of this cell, delete these cells as well. You can do so by pressing Control M and D, and over here, inside the cell, we will first obtain the model parameters by unpacking model.parameters into a list of two elements, W and B. And before proceeding any further, it seems that none of our cells are run, and I'll just go ahead and add a print model in here to see an output. But aside from that, let's rerun all of our cells to ensure that everything goes by smoothly as we go along. All right, back to it. We were unpacking model.parameters into a list of two elements. Don't forget your brackets. And now printing W and B. And we see that the weight is a two-dimensional tensor with one row and one column. So we can access this weight 1 is equal to the weight at row index 0 and column index 0. And same thing for the bias term, except it is only a single dimension within the 0th index of our tensor, B0. All right, and printing both values, print W1 and B1. We obtain them, let's remove that. We obtain them as a tensor type. We can actually add .item to both terms, and what that's going to do is give us a Python number from both tensor values. Outputting this, we get our parameters. All right, and let's make this into a function for cleanliness. What we can do is write def get params, and this will return the two values as a tuple. It will return w00.item as well as b0.item, removing the following. Now on the next cell, we will plot our linear model alongside the data points. So we will call a function def plot fit. The argument it will accept is a title, where our plt.title will equal the title that was just passed in. And now since matplotlib is most compatible with NumPy, let us first actually, on top, import NumPy as NP. We know the equation of a line is also y is equal to wx plus b. We have w, we have b, as they were initialized once we created our model. So what we can do is determine numerical expressions for x1 and for y1. So first what we do is we set w1 and b1 equal to the return value of get params. Our x-axis seems to go from -30 to 30. So what we can do is simply set x1 is equal to numpy.array -30 to 30. Make sure this is an array, not a tensor, to ensure compatibility with pyplot. And now from these two x1 points, going from one extremity till the end, we can get two y points. We can compute y1 is equal to w1 times x1 plus b1. Ultimately, this will return two y1 points, one at -30 and another one at 30, which will be connected by a line, hence plotting our linear model. All right, let's plot it. plt.plot x1, y1, and given that our data set is blue, let's plot it as a red line by specifying the string r. All right, and that's it. Now we also want to plot our scattered data points, and we do this with plt.scatter. We will plot X and Y. And finally, showing our plot with plt.show, and on a new cell, we simply call plot fit, with the title being initial model. All right, plotting our model alongside the data points, we can clearly see that this is not the line that best fits our data. We will need to use gradient descent to update its parameters. We will start doing that going forward.